Hi, my name is Oxide. Welcome to today's video about the chemical element aluminium. In North America it's called aluminium. Aluminium has the atomic number 13. Its name comes from Latin alumen, which means bitter salt. It was discovered in 1825 by the Danish chemist Hans Christian Ørsted. And in nature there's only one isotope, that's the isotope 27. The other isotope 26 is radioactive and it's just in traces. Its half-life is 717,000 years. These are pictures of the crystal alum, which is a hydrated double sulfate of aluminium, left. And at the right there's chrome alum, which contains chrome 3 ions, and these ions give this mineral its purple color. These are two more aluminium minerals. At the left cryolite, which is sodium hexafluoroaluminate, and at the right corundum, which is aluminium oxide, and again the color comes from another ion, typically it's chromium. This is a picture of the periodic table. Aluminium is here, and the third group, in the boron group, and its origin is from exploding massive stars. This is a picture of the chemical elements in Earth's crust abundance. Aluminium is here, number 3, very abundant chemical element, and aluminium has a strong affinity to oxygen, which is number 1. This is the main aluminium source in Earth's crust. That's bauxite. It's an aluminium oxide with hydroxide, but it contains also oxides of other alchemical elements like iron, titanium, and silicon. This is a picture of our bauxite mine in Australia. This is the first step of a two-step process to produce aluminium metal, called Bayer process. And it's the extraction of alumina, aluminium oxide, from the mineral bauxite. First step is crushing, then it's heated with sodium hydroxide and filtered. After cooling you get aluminium hydroxide, and after heating of aluminium hydroxide you get alumina, which is aluminium oxide. Byproduct is red mud. This is a picture of red mud or bauxite residue storage in Stade, Germany. It is not clear what to do with this red mud byproduct. Maybe you could develop some building material out of this product. This is a picture of the Stromsvik aluminium smelter in Iceland. And this is the second step of the production of aluminium, which is the electrolysis of alumina. This is the process. It's called Hall-Heroult process. It's electrolysis of alumina with carbon anodes. And this gives you aluminium metal and byproduct carbon dioxide. Another important component is cryolite, sodium hexafluoroaluminate. It functions as a flux. It lowers the melting point. And byproduct is the carbon dioxide and fluorine compounds. They are problematic because they are strong greenhouse gases. That's why aluminium recycling is a better process to get back the aluminium metal. It saves about 95% energy versus new aluminium. You don't need the mining, you don't need the bioprocess, and you don't need the electrolysis process. Different countries have different recycling rates, and there's still a lot of room for progress. This is a picture of the world's aluminium production. In 2021, 67 million tons of aluminium were produced, and the number 1 producer is China with 39 million tons. This bus shows you one of the advantages of aluminium. That's the BYD electric bus in Eslöv, Sweden. And if you want to make an electric bus, you want a big range. But this means you need a big heavy battery, so you have to find ways to make the other parts lighter. And using aluminium is a good strategy because of its low density of just 2.7 grams per cubic centimeter. That's just 1/3 of steel. This is another bus. This is a diesel bus, Solaris Rubino 12 in Munich, Germany. Shows you another advantage of aluminium. This bus has two parted side panels, this white part and the blue part. And the bottom part, the blue part, is made of aluminium, and its purpose is to prevent corrosion. Usually corrosion starts from the bottom, but with these aluminium panels you can prevent that. This is how this works. It's called passivation. For this to work, the Pilling-Bedworth ratio is important. It's the volume ratio of the elementary cell of a metal oxide to the elementary cell of the metal. And in this picture you can see the three possibilities. If the metal oxide has too little volume, then if this ratio is too low, then you have gaps and the oxygen can corrode the metal underneath. If the ratio is too high, then you get this structure where the oxide layer can be peeled off. This, again, the metal can be attacked by oxygen. This ratio has to be between 1 and 2, and then it works perfectly, because now the oxide layer is like a layer of paint, protects the metal underneath from the oxygen in the air. And aluminium has a ratio of 1.28. That's why it works. This picture is of a Citroën Type H from 1981. It's made of CGI, corrugated galvanized iron. You can give iron a coat of aluminium and zinc and protect it from corrosion. The first aluminium car body was made in 1899. And there's a trick to make it work even better, and that's anodizing. This gives you a thicker oxide layer, gives you a better protection. This is a picture of aluminium can. In the world, 180 billion cans are produced per year. This started in 1957. The aluminium can is coated inside with lacquer or polymer. It prevents corrosion of the aluminium can. Aluminium foam can be made in different ways. You can use gas steams or blowing agents which decompose, or polyurethane, which burns during the process, or salt. Its advantages are it is durable and lightweight. Applications are, for example, for filters and heat exchangers. This is a picture of aluminium foil. It has a typical thickness of 0.02 millimeter. Its production started in the USA in 1913, and aluminium foil replaced tin foil in the 1950s. Tin foil had the disadvantage: it gave food a tin taste. This is an example of an aluminium alloy, 2024 aluminium alloy. Contains 4.5% copper, 0.5% manganese, 1.5% magnesium, and less than 0.5% silicon, zinc, nickel, chromium, lead, and bismuth. This alloy is very strong, and that's why it's used in aircraft. This is another use for aluminium. It's thermite welding, a Goldschmidt process. It is used to connect railway tracks. Iron oxide is reduced by aluminium. You get iron and aluminium oxide. And aluminium has a high affinity to oxygen. This reaction is highly exothermic. You have to be very careful, and that's why this works. This is a picture at the left of the mineral corundum, which is aluminium oxide, alum. Al2O3. At the right, that's the powder, white powder. This compound is used as filler for plastics in the glass industry and as abrasive because it is hard. It can also be used as a filter and as a catalyst. These are two variants of corundum. At the left, that's ruby. This was the first laser. It was a ruby laser. The red color comes from the chromium 3 ions. At the right, you can see a picture of synthetic sapphire. This is the Verneuil process. It was developed in 1883 by Auguste Verneuil. Works at a temperature of above 2000 degrees Celsius. This was the first commercial production of synthetic gemstones. And Auguste Verneuil was already in 1907 able to produce 1 ton of synthetic gemstones in 1 year. At the middle, this is this drawing of his apparatus. At the right, this is how it works. Hydrogen is burnt with oxygen. This makes the aluminium oxide melt. You create little droplets that drop on a rod. At this point, you get a single crystal. It slowly grows, and the crystal slowly moved away out of the hot zone. It reminds you a bit of the stone melting process in the refining of silicon. And you can make colored crystals by adding chromium oxide. This gives you red crystals. And with iron oxide and titanium dioxide, you get blue crystals. This is another important compound, aluminium sulfate. It is used for water purification by flocculation. The way it works is the tiny particles in water that are floating are stabilized by their charge. And this compound produces protons in water. These protons destabilize the tiny particles and cause aggregation. And this causes flocculation. And that's how this works. This an important compound in organic chemistry, that's lithium aluminium hydride, LaH, was discovered in 1947 and is used as a reducing agent in organic chemistry. You can see you can make amines from azides or nitriles or amides, or you can make alcohols from carbonic acids or esters, ketones, aldehydes, epoxides. This is the compound aluminium trichloride, AlCl3. It is used for the Friedel-Crafts alkylation and acylation reaction. These reactions require a water-free medium. And they were discovered by Charles Friedel and James Crafts in 1877. This is called an electrophilic aromatic substitution reaction. Because the benzene ring has a high mesomeric energy, it's a very stable ring. That's why it tends to substitution reactions over addition reactions. And that's how you can add this functional group, acyl group or the alkyl group, to this structure. This is the Ziegler-Natta Catalyst. It's titanium tetrachloride and diacyl aluminium chloride. It was used in the synthesis of isotactic polypropylene. And for this discovery, the Nobel Prize in Chemistry was given in 1963 to Carl Ziegler and Giulio Natta. In these pictures, you can see the 3 different versions of polypropylene. At the top, red is the carbon atoms and blue the hydrogen atoms. This group CH3 is called methyl. Methyl group is, if the methyl group is all on the same side, it's called isotactic. If it's alternating, it's called syntactic. And these both variants are crystalline compounds. At the bottom, that's a random distribution of the methyl groups. This is called atactic polypropylene. And this is known to be amorphous polypropylene. This is a nice picture. It shows a gentleman who has been foiled. And what I like about this picture is that he is smiling about it. He's taking it easy. That was today's video about the chemical element aluminium. Thank you for watching. Have a nice day. Bye-bye.